Hello, welcome back. Further maths, conics today. This is an exam question. I'm trying to do more exam questions. Just very difficult to actually put the text up there. We'll take the board. So I will try to explain what this question is actually saying. We have an ellipse and we have a hyperbola. Both of them only exist in the top, on the first quadrant, on the top right of your coordinate axis. A is bigger than B is bigger than 0, so these are positive numbers where A is larger than B. So this is what happens next. The tangent to the hyperbola, this is the hyperbola, at some point in the first quadrant passes through the focus of this ellipse, and we have to assume is the focus with the positive focus on the one on the right, because of course the two objects only exist on the top half of the axis, so they only live in here. So if the tangent to the hyperbola is passing through the focus of the ellipse, show that the gradient of the tangent has to be equal to 1. Okay. In my paper, I think I've done this in 3 bits in terms of structuring it to actually help you see what needs doing. Here we're going to do it as one lump. So it goes, well, the first thing we need to do is perhaps work out the equation of the tangent to the hyperbola. So that's the hyperbola in here, standard equation. So let's differentiate it. 2x, differentiating implicitly, 2x over a squared minus 2y over b squared dy by dx is equal to 0. Save myself a little bit of board rubbing, so I'm going to put equal there and move it to the other side. Lose the 2 and the 2 from each of these fractions, and then the gradient, quite clearly the dy by dx is going to be b squared traveling along, and the y will come down, so that's my dy by dx. So that's the gradient of the tangent to the hyperbola. We want now a general point on the hyperbola. To me, it makes more sense to go parametric here. The thing is, I've just forgotten which way the parametric equations, it's a sec and a tan for a hyperbola. So of course the identity that we need to be using is the 1 plus tan squared theta is equal to sec squared theta. But because we have it that minus that, so it's going to be sec squared minus tan squared theta is equal to 1. I'm trying to derive the parametric equations. When I was doing obviously this kind of stuff myself, I had all this in my memory. Now I forget, I have to derive things. I do apologize. Maybe you know it and you may be laughing at me, but here it goes. So this is going to be the parametric equations of a hyperbola, a general hyperbola. This is going to be my sec, and therefore it's going to be, for this particular one, a sec theta. That's a general point, and the tan will be the y/b tan theta. And of course, because it needs to lie in the top right on the first quadrant, because of these conditions here, quite clearly my theta is an acute angle here. Theta is between 0 and pi over 2. I'm not writing it up there, but I have this in my head. So I can find the gradient now at a general point. So dy by dx, let's say at the point where theta is equal to theta, it doesn't really matter what we're writing. So this is a gradient function, but this is not the gradient at the general point. It's going to be b squared x, so ab squared sec theta over, the denominator is going to be a squared b tan, which will simplify to, we can lose, of course, let me write it, b sec theta and over a tan theta. Does that simplify? That's a 1 over cos and 1 over cos, so it will simplify. I cannot see it, sorry. I'm going to write it as b over a The sec is 1 over cos. The tan needs to go to the top, it'll become a cot, and a cot on the top, it'll become a cos over sine. So this is going to be, of course, b over a, and the sine is at the bottom. So I'm going to rewrite this. I hope you follow what I've done there. Take your time, obviously, to simplify. B over a sine theta. So that's the gradient at the general point on the hyperbola. Now we need to find the equation of the tangent. So the equation of the tangent should be y minus the y coordinate of my general point, y minus b tan theta is equal to the gradient tangent b over a sine theta, x minus the x coordinate a sec theta. Now, do I need to tidy this up? Let's have a little think about what we need to do. What did the question say? We have the hyperbola. At the general point, we're going to take a tangent, and this tangent is passing through the focus of the ellipse, and the positive focus, because of course the rest of the ellipse is not there. Okay, what's the focus of the ellipse? The focus of the ellipse in general form, if it's in standard form, is going to be AE, 0, where of course E is not an exponential E, it's clearly the eccentricity of the ellipse. Okay, so if it's passing through this point, that has y is equal to 0, so I can get the x coordinate in terms of some kind of trig. So I'm not going to simplify this. I don't know if you follow what I'm doing. I can simplify that, get a nice and neater expression for the equation of the tangent, but this particular tangent, that's the equation of it, is passing through the focus of the ellipse, so it's passing through here. So when y is equal to 0, I want to see what is the x coordinate on this tangent. So we're going to do that next. Y is equal to 0, of course, going to give me minus b tan theta is equal to b over a sine theta x minus a sec theta. We're going to get rid of the b's, divide both sides by b. Let's not lose the minus though. Okay, that is going to simplify now to times that across, minus a sine theta times the tan of theta. So that is going to be equal to, let's write in sines and cosines, and if we go back to tans, it doesn't really matter. Sine theta cos theta, that's that tan there, that being times across, is equal to x minus minus a over cos of theta. Okay, so what happens now with this particular one? Our x, I'm going to leave it on this side, is equal to, this is going to go to the right, so we're going to have a over the cos of theta, this is this term here, minus a sine squared theta over cos theta. And I think this will simplify, won't it? Because we're getting there a 1 minus sine squared. Hope you can see it. This will simplify massively, in fact. Let's write the x on the left. Factorize an a on the top. We have already a common denominator. So that's, of course, a cos of theta. 1 minus sine squared theta. And this will be a cos squared over cos theta, so x will be simply a cos theta. Okay, let's collect our results so we don't lose information. Tangent to hyperbola to capital H passes through the point a cos theta comma 0. Okay. And this point here, this coordinate rather, not this point, this a cos theta must be the same as AE. So that means the eccentricity, consequently, of the ellipse by comparing this, E must be cos theta. Okay. What's the eccentricity now of the ellipse? Eccentricity relation for, it's in the formula booklet. The ellipse has eccentricity less than 1, and the b is the smaller number. So b squared is equal to a squared 1 minus e squared. I believe that's correct by common sense. Okay, so what we're gonna get there is b over a all squared is equal to 1 minus e squared. And annoyingly, I rubbed off something that I should have had up there, and I don't quite remember it now. Don't tell me I have to differentiate it again. I feel like pulling my hair now. Okay, we'll patch it up. We have b over a all squared. Just divide that. Is 1 minus e squared. So of course my e is of course the cos of theta. So b over a all squared is 1 minus cos squared theta, which of course my b over a all squared will be equal to the sine of theta, and squared of theta, and therefore b over a is going to be positive sine theta, because of course a and b are both positive numbers. So far so good. But now I don't have the gradient of the tangent. I rubbed it off and I can't remember if it was, I know it was in the bottom, it had sine theta, and I can't remember if it was b over a or a over b. It's okay, just to convince you that I think that's done now. I hope it is. I'm gonna have to differentiate this again, unfortunately for me, and unfortunately also for you watching this. I'm differentiating the hyperbola again because I need the gradient at that particular point. So it's going to be 2x over a squared minus 2y dy by dx over b squared is equal to 0. Call it equal, lose the 2's, and then the dy by dx was going to be b squared x over a squared y. And now we need the parametrics of the hyperbolic parametrics, and again I forgot what it was. I think the sec minus tan squared, that means the x, it's the sec. So that turned out to be at that particular point. Sorry, I'm writing very sloppily here. I did derive all of this kind of stuff up there. I just rubbed it off, and it's very, very annoying. We got b squared, and that was an a sec theta, and that was an a squared. The y was b, that was a tan theta, and we ended up with, in fact, b over a. We got more b over a, and we end up with over sine. So that was the gradient of the tangent to the hyperbola at the general point. So if you look now, this is the gradient of the tangent, grad of tangent, and I think we're done. That's very, very bad planning. It just actually gets to show that I'm not improvising stuff here. I'm not one of the celebrity YouTubers that kind of edit the videos. They as they come, and often I do stupid and annoying things. So this is the gradient of the tangent to the hyperbola. And if you look at what b over a has to be, if this tangent goes to the focus of the ellipse, b over a must be equal to sine theta. And look at this, b over a is in fact sine theta. So you can write this as b over a times 1 over sine theta, which of course is equal to the sine of theta times 1 over sine theta. And I think what the question was actually saying is, if this is to be the case, then the gradient of that tangent has to be equal to 1. Okay, I wish I could say who's laughing now, but I'm not laughing. I'm absolutely stressed out. Till next time, I hope you enjoyed it though. Bye.